But the first thing I want to talk about, and this I kind of go over this again every time I bring up a discussion about soil testing, as to how to take a sample and make sure everybody's on the same page, and emphasize the importance of soil sampling. Basically, what we want to do is try to take 15 to 20 samples per designated area. Now, that may seem a lot, and usually that can range anywhere from, say, 5, 10, 20 or so samples per designated area. So your designated areas would maybe be situated like this, where the green areas would be one type of soil type, for example. The red areas would be a different type of soil, or a different kind of vegetation or slope or something like that. So then you take samples from these areas separately and submit those for analysis. You want to take the samples and again, this is where it's a little different from ag versus soil health. Ag will usually go to a depth about 6 to 8 inches, and maybe a subsoil sample to about 24 inches or 18 inches. So, and when I say subsoil, I'm referring to soil below the surface. So we take a 0 to 6 and then 6 to, say, 18 or something like that, or 6 to 24 type sample. Subsoil doesn't mean like some people kind of get that confused with other terminology. Anyway, combine the samples in a plastic bucket, collect enough sample to mix it up and really well, and then take about 2 cups, submit about 2 cups for regular routine analysis. But if you're going for soil health analysis, then bump that up to about 6 cups, 6 to 7 cups, because there's a lot more testing involved with that. And it uses more sample in that type of analysis. So just keep that in mind. I usually emphasize this because sometimes, it doesn't happen as much as it used to, but people would, they got to get a soil sample in, so they drive down the road, they jump the fence and take a sample from the headlands of their property, submit the sample, and they wonder why the nitrate's like 250 parts per million. Well, because the fertilizer spreader did a turn at that point and dumped a bunch of fertilizer at that spot, and so you end up with a lot of nitrate or fertilizer that might skew the results. So put some time into this. It's really pretty important to interpret results. Fill out an information sheet as much as you can. This helps us make recommendations to grow the crop. So we're looking at irrigation types and plant types, potatoes or alfalfa or whatever you're trying to grow, and then possible yield goal that you might shoot for, and then any other information more that you might put on, any kind of organic products you might be putting on, because we'll take those into account when we do our nitrogen recommendations, because we do consider about 1% nitrogen in manures, for example. And so we'll consider that. We'll knock off that nitrogen contribution from manure in making our recommendation. So fill it, whoever lab you're working with, you should fill out that information as much as you can. Other things to look at for soil health or assessment types of things that you can do, just like visually looking at your site. Things like looking at numbers of earthworms, organic matter color, organic matter roots, residue, subsurface compaction. You can get that with a penetrometer right in the field. Erosion, water holding capacity. You can simply look at how much water soil will hold just by adding some water to some soil in the field or something. Drainage, pH, tilth, viability, how much of the soil will break apart, and then crop condition. These are some of the things that you can look at. There's NRCS has a 100-page document on how to develop an assessment sheet. So it really gets pretty detailed in some respects. Keep in mind that soil analysis uses very, very small amounts of samples. So we're looking at, for example, for organic matter, we use 0.5 gram of sample. So that 0.5 gram is going to be coming from the sample that you submit. And this is why you need to have a really good sample, because that 0.5 gram could could be, a few hundred square feet or a few square feet all the way up to 40, 60, 100 acres. So keep in mind that that is going to have to represent the organic matter in that, from where that sample is representing. This happens to be our organic matter test. This is our blank here, and this is the amount of organic. The organic matter tends to turn these green, so that the reaction as it goes from column 6 to column 3 and turns green with the reaction with organic matter. The greener the color, the darker the color, the more organic matter we have in there. Routine soil testing. The tests that are used for routine pH, for example, are usually a 1-to-1, so 1 part soil, 1 part water, 1-to-2, or 1-to-5. For soil health, it's usually a 1-to-1 basis on a routine basis. The 1-to-1 mixture is a good way to quickly look at pH and also conductivity because it can be automated. You can set up 100 samples in a robotic type machine, and you can do a lot of samples very easily through robotics. The problem is when you have a 1-to-1 pH that is more than 8.5 or more, then that indicates the possibility of acidic soil. So in that case, then we have to go back. What we'll do is we'll go back and make a paste out of the sample, because usually on a paste basis, the pH is lower. And if the pH is still high on a paste basis, we'll go ahead and do a sodium absorption ratio on it, because it usually indicates the presence of sodium in sodic soil. Then for electrical conductivity, same kind of thing, 1-to-1, 1-to-2, or 1-to-5. And again, the 1-to-1 is real convenient. It can be automated. But the paste values really do represent the field conditions. So if we have a 1-to-1 conductivity that's 1.2 millimoles per centimeter or more, then we'll go ahead and make a paste out of it. And then we'll evaluate that on a paste condition. So if we get a value of 7 or more on the paste, then we'll go ahead and do a sodium absorption ratio. Again, usually indicates high sodium, and we usually need to evaluate the SAR. Again, the 1-to-1 values tend to be lower than the paste value, so that's why we have to do the paste to evaluate it further. So those are the measurements for that, the limits for that. You may also see something like a buffer pH on your soil reports, and this is related to evaluating the soil for lime application. It's not often we get a lot of samples that have a really low pH, but when we do get a sample that has a pH less than 6, then we'll do a buffer pH on it, and that will tell us how much lime we have to add to the soil to bring the pH at least up to 6. But we make recommendations for 6, 6.5, and 7 to get to those pHs. So again, if you see that on the report, that's what that's referring to, a buffer pH. Excess lime is something that we do, and something we actually do in the field, but it tells us how much residual, what we call residual limestone, is in the soil. Lime can exist in the soil in very, very small particles, as calcium carbonate or magnesium carbonate. And so it doesn't really, affect the nutrient value in the soil in terms of it's just being in the soil, but it does influence the way they may want to treat the soil if you want to try to lower the pH, for example. So if you have a lot of lime in the soil, usually more than 3%, and lime can go anywhere from no lime in the soil up to 30 or 40%. So if you have a lot of lime in the soil, you're going to have a really, really hard time lowering the pH, because you have to start adding acidic materials like sulfur, acidic organic matter. You may want to use ammonium fertilizers, but that's not organic, so just don't even think about that. So, but ammonium fertilizers will help decrease the pH. So, but if you have a lot of lime there, it may not work very well. So it's best to either accept the fact that you have a high pH with a lot of lime in the soil, kind of work with it around that. Work around that. And plants grow fine with lime in the soil and a little higher pHs. Typically, our pHs run around 7.2 to 8.4, and plants grow fine. They do okay. Naturally, you would like to have pHs that are running 6.5 to 7.2. That's where most of your nutrients are going to be available. But in the scheme of things, and you can try to lower, make the effort to try to lower the pH. And in some cases, under very high value crops like pecans in Arizona, they'll actually inject sulfuric acid in the soil to neutralize the lime and get rid of that caliche layer, which is that calcium carbonate layer below the soil surface. And that might be out of way out of the scope of what you might be able to do. But again, it's very difficult to lower the pH on a high lime soil. Texture estimate, we use a field method. This method is just pressing some damp soil, wet soil between your thumb and forefinger and seeing how long the ribbon is and then how coarse the soil feels. So if you have a short ribbon with a coarse feel to it, you have a sandy soil. If you have a 2-inch ribbon and it feels very slick and very smooth, then you probably have full-blown clay soil. Then you have everything in between. So if you have a 1-inch ribbon, you have a clay loam, sandy clay loam, or silty loam. So we use that in the lab to give us an estimate. You generally have to get some pretty good experience doing this, but you can tell a sandy soil from a clay soil. I mean, it's pretty obvious to do that. It's trying to get down to the sand content and the clay content, which makes it a little more difficult. We can evaluate things like drainage. So if you have a clay soil, things aren't going to drain as well. You can give an estimate of CEC, because if you have a clay soil, your CEC is going to be a little higher than with a sandy soil. And then you can get an idea of whether or not the soil is suitable to try to reduce salts. Are you going to be able to add irrigation water to try to move water through the soil and get rid of those salts? So it gives you a general idea of the status of the soil. The sodium absorption ratio, this is a comparison or relationship of sodium to calcium and magnesium. These are all in milliequivalents per liter. That's just a measurement term. This is not base saturation. These are not exchangeable bases. These are the cations, which are sodium, calcium, and magnesium, from a saturated paste. So you'll see this on our soil report. Some people kind of interpret that as base saturation or exchangeable bases, when actually it's not. It's the quantity of these analytes that are used to calculate SAR. And so if you have an SAR that's 15 or more, then you're going to have an unstable soil, probably a sodic soil more than likely. And the soil isn't going to drain very well. It's going to be very compact, and you won't get water through it very well. Roots won't grow very well. The plants generally just die. And it's a tough thing to try to reclaim. If you have a low SAR, less than 6, you generally have a more stable soil with less sodium influencing the soil structure. To reclaim a high sodic soil, we have to make a gypsum or an elemental sulfur recommendation. So we'll evaluate the SAR, we'll report that. If it's more than 15, then we also supply a gypsum or sulfur recommendation to try to repair the soil. And then we have to have calcareous soils to use sulfur, because the sulfur will produce very dilute amounts of sulfuric acid and neutralize the lime in the soil, and that will help to free up calcium. The whole idea is to add gypsum, which is calcium sulfate, or free up calcium with sulfur, and then flush the soil with water if you can get water to move through that soil. And the calcium will replace the sodium on the exchange sites, and then you flush the sodium out of the root zone. Then the soil will become more permeable, and plants should grow better. They should. But usually we'll recommend a total amount of gypsum or sulfur. We'll usually say put on a third of it and then do your reclamation, add the water, see if it's working. If it's not working, then you may be up against a wall about trying to reclaim the site. But usually we start off small and then kind of work into trying to add enough gypsum to get it to reclaim. Organic matter and soil organic carbon, a big part of the soil health. We use typically labs will use a method called Walkley Black or a modified Walkley Black. The Walkley Black is what we call a titration method. The modified Walkley Black is where we've taken the Walkley Black method. We do a colorimetric, which is a lot faster. So you might see that on a soil report, modified Walkley Black or something. That's just a method for organic matter. Another way to do this is weight loss and ignition. There are a number of ways, not a lot of ways, but a number of ways to try to do weight loss and ignition. And the idea is to be aware of, when you send it to a lab, be aware of what methods they're using, so that if you want to go to another lab, and sometimes this happens, you get kind of ticked off with the lab, and you think, oh, this isn't right, this can't be right, so I'm going to send it to another lab. And so you've got to be aware that they may be doing methods different from the other lab. So be sure to inquire about the methods they're using, so you're comparing apples to apples. But weight loss and ignition, the North American Proficiency Test Program, which is a program where they send us samples, we do the analysis, and they compare our results to 160 other labs in North America and Central America, and then they tell us how we're doing. And their method is 2 hours at 360 degrees, but Cornell uses 500 degrees C. The soil survey people with NRCS have a method for 400 degrees. So it kind of varies a little bit, but you want to be on the same page with what they're doing, so you understand what their method is compared to maybe what somebody else might be doing. Total organic carbon is a soil health method, commonly done by doing total carbon by combustion using a machine like this, and then subtracting off total inorganic carbon, which is measured by CO2 evolution. POXC, you may see this on soil health reports. This is permanganate oxidizable carbon, and is a measure of what's considered to be active carbon, the carbon most likely to provide nutrients to the plant as the carbon decomposes. So that's become a very popular method. It's pretty quick, and you may see this on a soil health report. Nitrate is, again, not really part of the soil health parameters that are measured, because they'll use bioavailable nitrogen. They call bioavailable nitrogen. I look at it more as nitrate and ammonium, but for nitrate, we use ammonium bicarbonate DTPA, which is a method we've developed at CSU. We've been using that since 1972, and we have a lot of data with regard to that. It's been calibrated well with crop response, and so we've been using it quite a lot. You may see another test for water extract. 2 molar KCl is another one, and also you may see something called a Haney test. So there's come out probably in the last 5 years or so. There's a person by the name of Rick Haney in Texas who developed the Haney test. It's caught on quite a bit, and he's used it quite a lot for it, and it has been picked up by other labs. So they're using it as a multi-element extraction. The idea behind the Haney test is that it's going to simulate what roots see in the soil. So he uses 3 organic acids to extract the nutrients from the soil, and then compares that to plant growth. The problem with the Haney test is he hasn't calibrated against crop response. He has calibrated against other, or correlated against other nutrient extractants, but it has caught on quite a bit. So you may see something like the Haney test by itself, but you may see the Haney test soil health test, which is the Haney extraction plus the POXC plus the organic matter plus the bioavailable nitrogen plus all these other things that kind of go into soil health. For phosphorus, phosphorus is an element that has a lot of extractants. We use ammonium bicarbonate, DTPA. There's also sodium bicarbonate, which we put on our soil tests because people are used to seeing that. So we put that on our soil tests as well. There's the Bray-P test, and then the Morgan test, done in the Northeast, Cornell, Maine, New Hampshire, Vermont. This is the Morgan test. There's a modified Kelowna test, which is used up in British Columbia and Canada. Mehlich test is caught on quite a lot. Mainly designed for the South, Southeast, but some labs will use it out here. The problem with the Mehlich 3 is that it's a very strong acidic type of extractant, so it's going to dissolve calcium in the soil, so it may get bumped up calcium numbers on that. And it's not well correlated with phosphorus in a calcareous soil. But a lot of people use it because it's really easy to use it. You can make up a big batch of it and store it and then use it pretty easily. It's a 5-minute extraction, so it's quick and easy. And then also the Haney test for phosphorus as well.
What's the best one for this area?
Probably, I think the best one is either ABDTPA or sodium bicarbonate. Some people aren't used to seeing ABDTPA, but sodium bicarbonate definitely is a better test. The thing about, there's a relationship between these two. The sodium bicarbonate will extract about twice as much as the ammonium bicarbonate. And all of these are going to give different numbers for phosphorus, because phosphorus extraction, the result for phosphorus is actually an index gauged to your crop response. So we use, and the convenience with sodium bicarbonate and ABDTPA is there is a pretty good relationship with that. So you can easily compare the two, and then you can also use our recommendations from CSU to determine the phosphorus recommendation from there.
It's important to know which test you use so you don't just follow recommendations.
Right. Right, yeah. So if you're doing, if they've given you a Mehlich P, make sure that you're using a calibration for fertilizer application gauged towards Mehlich phosphorus, which they should be doing. If the lab is doing it, they should be gauging it towards a Mehlich P calibration. Let's see. Potassium, ammonium acetate is a typical extraction, ammonium bicarbonate, DTPA, and also the Haney test. The ammonium acetate is probably the most popular one. Our test, ammonium bicarbonate, DTPA, gives the same amount as the ammonium acetate. When the ABDTPA test was developed, it was correlated to ammonium acetate, extractable potassium, the Olsen P test, and then also the 2-hour DTPA for micronutrients. So it's correlated to those 3 tests. And for micronutrients, we use the ABDTPA. Common one is 2-hour DTPA, and then the Haney test at Mehlich 3. So again, be aware of which test you're going to use so you know what you're looking at relative to crop response. And if you're trying to make comparisons, make sure that you're aware that the other labs may be doing something different. For soil health testing, there are a number of tests that have been tried. The ARS wet macroaggregate stability test, the NRCS wet aggregation test, the Cornell sprinkle infiltrometer test. The one that's most that is being endorsed for testing is the ARS wet macroaggregate stability test. Basically, this tells us how well the soil clods stay together as a result of being exposed to certain sieve types and water. The general microbial activity tests. There's the two tests that have been evaluated are the CO2 Respire, the 4-day incubation test, and the CO2 Respire, the 24-hour incubation test. The soil health testing is endorsing the 4-day incubation period. There is the 24-hour incubation test that you probably heard of, the salt beta test. We use that because it's really quick and easy. And also, because all you do is you put a little paddle into a sealed container and let the CO2 react with the chemicals on the paddle. It changes color, and then we have a color reader. You stick that in there, get milligrams of CO2 per gram per hour or something like that. So it's really quick, but this is a little bit shaky, but it gives you a general idea of what is happening. There's also enzyme activity. All of these enzymes have been included in the soil health testing process. And the first two are mainly for nitrogen carbon decomposition and conversion to available forms, the phosphomonoesterases for phosphorus, and the aryl sulfatase for sulfur. So all of those have been designated as enzymes that are part of that whole soil health testing scheme. The carbon pool, again, I touched on POXC. That's the one that is most likely to be used. It's simple, it's easy to do, it's quick. There are other methods that have been proposed, particular organic matter, the 28-day seed mineralization test. Some of these are lengthy, or the results haven't been, not enough results have been developed. Soluble carbohydrates, substrate-induced respiration biomass, carbon, those are all research methods at the bottom there. So the permanganate oxidizable POXC is the one that's most likely to be used. Bioavailable nitrogen, the autoclave citrate extractable protein content test, or ACE test, is the one that is, again, the soil health people are most interested in this. There have been other tests, cold water extractable test, not enough data for that. The short-term seed mineralization needs to be evaluated more. The 7-day and 28-day aerobic and anaerobic mineralizable N are pretty lengthy tests. The Illinois soil N test is basically just nitrate ammonium, and that's it's more evaluated against yield rather than soil health. I'm not sure why that. I think the main thing with that is that you're not getting more organic nitrogen out with that. And then enzyme activity and protease have their disadvantages to use. Microbial diversity, there's a phospholipid fatty acid test for that. It's kind of expensive. Not a lot of labs are doing PFLA. You got to realize that this test gives you communities of bacteria, and gram-negative, gram-positive bacteria. They don't tell you whether you have an ascomycete or bacillomycete or some type of organism in there. They'll give you colonies and populations. So it's going to be telling you whether your populations are shifting or whether populations are increasing or decreasing. It's still, this whole process still needs to be worked on, developed more, so we're getting a little more specific about if they want to, if this is where soil health wants to go, which I think this is probably something that still wants to be examined, that more work needs to be done on this to try to get more specific about the types of organisms in the soil. That's what people are really looking for. You know, is my mycorrhizae okay? Because when I talk to people, they're like, well, I want to add 10 pounds of mycorrhizae fungus per acre, and it's like, well, I try to talk them out of it because it's really kind of an expense you really don't need to have. But that's kind of what they want to see. They want to see, well, is my mycorrhizae increasing? Are my ascomycetes increasing or decreasing? Things like that. And when you tell them about PFLA and what it's going to give, it doesn't really tell them the average person. If you're a researcher, that might look okay, but for the average person, it's something that they don't can identify with.
This would give you your fungal bacterial ratio that we're talking about now.
Well, that's the problem. It may not, and so it may give you a total fungal population kind of thing. You could probably use it in terms of that and compare it to other types of colonies or communities of bacteria. So you might be able to get like a total fungal type community colony kind of value versus your other type.
And it's going to be by mass. And when people talk about the fungal bacterial ratio that is getting a lot of interest, is it by mass?
I would guess it would be by mass.
It is by mass.
Yeah.
Not particular enough.
Yes.
Yeah.
And this won't give you mass, right? Or does it?
No, it should give you mass.
Yeah, actually, yeah.
Okay, so it could be, okay. But it's not very specific. It's just all fungus and all mass.
Correct.
Right.
Thank you.
And then you may also see this called alphane here, consistent with PFLA. And both of these are both being worked on quite a bit to develop more usable information like that. So probably see more of this developing later on.
When you're talking about that prolific test, what are the actual units?
That's a good question. I'm not sure what it is. I think it's probably colonies per mass of soil, something like that. I guess.
So the PLFA, the ratio, it's a ratio, it's a mass ratio. Plates would be called forming units.
Okay.
So it's unitless?
It's going to be, you have a certain amount of fungi per gram of soil. And it's going to be on a by weight basis. So, and I'd have to look at the publication to be able to, because that wasn't my area.
Micrograms per gram of soil.
Yeah, something
Something
like
like
that.
that.
And it's a ratio, so it doesn't tell you numbers, because of course bacteria are going to weigh less than fungi. So it's not going to tell you a cell basis, it's going to tell you a mass basis. If you did total number on plates, then yeah, that's colony forming units. And on plates, you only get 2 or 3% of what's in the soil.
Another soil health parameters is aggregate stability. You can see with long-term grass side, we have much greater aggregate stability here being retained, the soil being retained at 5 millimeters, not 5 millimeters sieve, versus cornfield with a conventional type tilling, where we're seeing the soil highly dispersed and being able to flow through different sieve sizes. So you can see the advantage of the long-term grass sod condition being a lot more stable than conventional tillage methods. Available water capacity. This is where we put soil into a pressure containers, vessels. So we'll have a 15 bar pressure set up over here, which is 220 pounds per square inch, and then we have a third bar over here, which is 14 pounds per square inch. They'll apply pressure to these, and the soil's inside of this. Maybe kind of able to see the samples are in here in little rings, and they're saturated with water. We'll apply pressure to these, and then get the water content in the soil that's in the third bar, and the soil that's in the 15 bar. The water in the soil in the 15 bar. The difference in the water content between the two is your available water content. And so that's basically a difference between field capacity and Bulk density, something can be done easily in the field. Taking a cylinder, pressing it into the ground or pounding it into the ground. You'll have your volume, because bulk density is grams per cubic centimeter. So you have your volume. You'll have to take the soil and dry it out like a muon or something, and then you'll have the weight of your soil. So you can easily do this in the field if you have a little scale or something. You can use this. So bulk density of 1, you can have much more pore volume. Looser soil, bulk density of 1.4 is going to be more compact. Clays tend to be higher bulk density than sands, obviously, because of the nature of the sample. And so it's a good way to evaluate compaction and make comparisons between sites, for example. Infiltration, something that can be done, again, in the field, placing a cylinder in the field and then putting this right on top of bare soil. We've got a lot of residue here, but putting it on top of bare soil, adding water to that, and then see how well the water will go through into the soil. You time that and get a volume of the amount of water that's going through. Some people will actually just dig a hole. So you have a square foot, a cubic foot hole, for example, fill it full of water, and then see how fast the water will go through or drain into that site. So you can easily do that in the field. Slaking is something that is not as popular as the soil health process, but is something that might come up. This is a soil that from a grass type natural environment. This is with conventional tillage. You can see the soil is holding itself up together a lot better here. The soil is being suspended into a cylinder of water. And so this is holding it together a lot better, and this is dispersing. Same kind of thing with the aggregate stability kind of thing that we saw earlier. And then soil crusts. This is something kind of visualized in the field, something kind of try to minimize with that, adding a cover to the soil, keep the moisture from evaporating from the surface. Conclusion, basically what you want to do is spend some time taking the soil sample. The other thing is when you're sending a sample to the lab, make sure you're aware of where you're sending the tests that are being done by the lab, type of tests that are being done. Also assess the site for visual soil health conditions. You can utilize basic soil analysis and incorporate the soil health testing into the whole process to help improve yields, to monitor management practices that will help to maintain a healthy soil. And then the biggest thing is maintain records with soil test management practices. Because when you're doing organic certification, you're going to want to be able to produce things to your certification agencies so that they can see that you're making some effort to maintain soil health and ensure organic practices. So that's pretty much it.
Thank you.
Questions? Yeah.
So, for, like the water infiltration test in the field, are you, like if you're inserting like a PVC pipe, like how deep you need to go? Because are you looking at like vertical movement of the water in the soil, or like are you taking into account like horizontal flow? Yeah,
well, yeah, and that's a good question. You probably would want to bury that to say a foot or so if you can. And that's why a lot of people just dig a hole too, and then they'll measure the size of the hole and then pour water into it, see how well the temperature will be. Because and in that case, you're going to have water going sideways and diffusing to the sides of the hole. So
If you're just trying to do just a quick and dirty demonstration, use a number 10 can, a large coffee can, and pound it gently into the soil. You know, if your soil is dry, forget it. You can't do that. Wet, or at least moist. And then you can timing comparison, but it's not going to be, if we were doing it for research, we'd use a double ring infiltrometer and let it set for at least 24 hours.
And for folks who are plowing more often, do you have an issue of running into a plow pan? Your homemade infiltrometer.
You might, plow pad's usually 6 inches, 16 inches, that would probably hit it just right there. But that's going to show up in reduced infiltration rates.
Okay.
Irrigation pipe works, 6-inch irrigation pipe works really well.
There you go, especially if you have a leveled edge.
NRCS has a big thing with something into again, the detailed practice. I think they're like 5 inches deep, you bury it 3 inches above, something like that.
Yeah, the NRCS has a whole thing on this, on how to make all these soil health field testing equipment available, so you can make it all yourself.
So you said you were doing the texture by hand. Is that in the lab you're doing that?
Mm-hmm.
Okay, so you're not doing a hydrometer test.
Yeah, well, we do texture by hand on a routine test because it's real quick and easy.
Okay.
We also do a hydrometer test for same set. You have the client ask for that.
Okay.
So we do have that. It's $20. And we do a lot of that. We do a lot of hydrometers. Seems like
Says the infiltration and the bulk density testing are used in the field. Are there any others that can be done in the field or in a home setting?
Well, you can look at the slaking test. I mean, that's pretty easy thing to do. Aggregate stability, you can get some sieves. You can do that on your own as well. A lot of the physical stuff you can do on your own. pH, you can get a pH, an inexpensive pH meter and conductivity meter. There are field nitrate tests. The Solvita test, you can do that. I think the Solvita test is a little pricey, because each one of those panels is $10.
Well, but you don't have to, you just use a canning jar and
right.
a little, I mean, what's in the recommended methods? It's just using a canning jar
Right. Yeah.
and a little beaker of hydroxide and
Right. So you can get that pretty easily.
and
Those are readily available.
and a whole lot cheaper than those Solvita pads. Even Ricken's not using those Solvita pads.
Someone your patent's gonna run out, right? Doesn't it expire at some point?
Yeah, but I think they're tweaking things.
Yeah.
But they're just too expensive.
Yeah.
I've gone round and round with the gentleman on the Solvita. But USDA will not, or the NRCS will not proprietary methods.
Yeah. Well, you can also get like segment
Drager tubes,
or Drager tubes
let's get a little price.
trap CO2 if you want to do organic carbon.
You can actually build your own meters and just see what happens with meters. Put the soil in them and just hook it up to a monitor and see how much CO2 is produced. You can create those pretty quickly.
Mm-hmm.
So back to your first slide and the soil sampling methodology. If we follow those, how much sample error is still inherent in this? And we go through this whole process, we follow a set of guidelines, but if we were to take a sample 6 inches over, would it be something strikingly different?
It's all variable. I mean, you're trying to minimize the variation of the lab in the field, but sometimes fields are real consistent. I've seen soils from Illinois where the guy sent in 100 samples. I swear that we got almost the same results for 100 samples. And I've seen soils from areas out here in Colorado where the soils are all different. from the same field. And so you're trying to do your best to minimize whatever variation is in the location that you're trying to sample. And you try to minimize that variation by taking more samples from that site, combining them, or being consistent with your depth. If you go an inch or two deeper or whatever, it probably isn't going to make much difference for one or two samples that you've taken. But it's all quite variable, and we're trying to minimize the variation. And I tell you, there's probably 100 papers out there on how to take a soil sample, and they all have a different kind of scheme on how to do it. And I think the best thing to do is just visualize how you want to, the site that you want to sample. Just go around randomly, take samples from the site. Statistically, you're supposed to take about 40 samples per acre to try to reduce that variation. And nobody in their right mind is going to take 40 samples per acre. But you try to do the best you can with the time that you have and the available equipment you have and the type of soil. Because if you're out there with clay soil, it's all dry, you're going to be using a pickaxe to get it out of the ground. So, and then it's like after the third sample, you're going to be like, this is crazy. So, it's that kind of thing kind of things.
Would you apply any sort of a discount to those recommendations based on any sort of standard estimation of sample area then?
We have to go with well, you mean in terms of what we would do in the lab or something?
No, I'm saying as a producer.
Oh, as a producer. Well, yeah, I think as a producer, you probably would want to look at that in terms of, what's the context of how I take the sample? Did I take a 6-inch sample? Did I only get 3 samples from the site? Whatever. So we'll look at it within that context and think that, okay, I'm good. And really, that's all you've got to work with. Then you're pretty much going to have to, either go with that or you're going to have to visualize, well, maybe as I go down further south on this site and it starts to slope away, maybe I'm going to have a different nutrient content in that soil. So you can kind of maybe guesstimate that might be a little different. You can factor that into your overall fertilizer program or something.
You're going to want to take still samples before and bulk them. You can take it from 20 expands and bulk them so you get an average. Unless you think there's a specific problem or specific area of your field, have such a sample.
So we geolocate our samples. We sample every year. Do you think that there is changes that we're able to influence the soil year to year and those changes are real, or do you think that would be like we just sample error based on,
I think
again, it's geolocated, but still.
Yeah.
There's still going to be some sample error there.
There's going to be some variation just based on the time of year you do it.
We try
If
to,
it were
within a
me-
month, we try to do it.
Yeah, if it were me, I'd do a baseline and then I go back and do it out here about every 5 years. If I was in the Midwest, every 3 years. But I'm sorry, but management changes are going to show up faster in the more humid areas than they do out here.
Yeah, but in terms of like aggregate stability and physical properties, you're probably not going to see a lot of difference, but you might see a lot of difference in nutrients.
It depends what shape your soil is.
Well, if you're consistently doing soil health, healthy soil management
Then
practices,
it's not going to change.
you may not see it.
But if you're starting from a soil that has been tilled until the deep down, and you start implementing soil health practices, you can actually see some significant changes within a few years. It's amazing how fast.
So when you have these nutrient analysis done, right? I know you can give recommendations on how much all that per acre to apply, but do you have something like that would also be able to recommend like cover crops and the benefits those give, or say actual organic type of addition like compost or wood chips or some sort of mulch?
Yeah, usually what that's based on is we usually have to rely on the client to make the decision on what they want to do, because there are a lot of different cover crops you can use. You can use ryegrass or vetches or beans or whatever it is, a cover crop. So that's a legume versus a non-legume, or what compost are you going to use? Is it manure? Is it cow? Is it sheep? Is it whatever? Or is it things like blood meal or cottonseed meal or alfalfa meal or something like that? So those are the things that you have to kind of manage yourself. I mean, if a person said, okay, well, I'm going to use X tons of cottonseed meal and blood meal and this and that, whatever on my field, then we can, as a person who's giving out recommendations, I can make a recommendation based on that. But if I don't know that, then I'm just going to go straight, add on 100 pounds of nitrogen. So the 100 pounds of nitrogen could be coming from an inorganic fertilizer or an organic fertilizer. If you're using organic fertilizer, then you have to decide which ones you're going to be using. The average, you can take an average of what those organic fertilizers are going to have. Blood meal's got about 12% nitrogen in it, but then only about 15 to 20% of that is going to be available for the first year. So you have to factor that in. So again, the huge amounts that you have to put on, or you may want to spread out the application over time. But those are things that we can do in the lab if you know what's being put on, but it's something that as a grower you would have to make those decisions. You can make those decisions as well.
To get more, I guess, if you're starting like in a new area that you're trying to reclaim or improve, you're starting to work on that may have been used for something else for a long time.
Mm-hmm.
Trying to figure out what's going to be the best course, I guess, on that.
Mm-hmm. Yeah. So I would get some baseline information first, and then go from there. What you want to add, how you want, what your objective is, and then go from there in terms of materials, what you want to use, and concentration. Do I want to bump up the nitrogen real quick? Do I want to use something that's going to be high in nitrogen to begin with, or do I want to pace it, increase it slowly or something like that? So it's if you put on too much manure, you're going to get salts in the soil, so you may want to spread out that manure application over time or something.
So for your biochemical and microbial indices, do you give people advice about how to sample and how to store the sample in order to deliver it to the lab? Or
well, we don't do any biological testing in our lab. Generally speaking, if you're doing biological testing, if I was going to recommend that, though, to send in a fresh sample, keep it cool, keep it cold, and then when we get it, we would refrigerate it, and then there's a lab on campus that will do PFLA or PLFA, and they, I would send a sample to them. If it was a long-term kind of thing, I would tell them to freeze the sample so they can sort it on that microbial activity.
Don't let it sit around like you might your regular soil sample. Send it overnight, same day. Don't let it bake in the vehicle. Make sure you've got a cooler out there when you're sampling. Don't let it heat up. The hotter it gets, the more changes there are.
And you'll see that a lot with if you see a sample that becomes really high in nitrate, sometimes I get ammonium mineralizing to nitrate. And so usually ammonia in the soils is, and this is why we don't report it here in Colorado, usually ammonium levels are like 1 or 2 ppm. But if you let that sit on the dashboard of your pickup, it'll just be 150 degrees in your pickup or something, and And that ammonia will mineralize to nitrate. So whenever we get a test for ammonium, we always tell people to keep the sample cold, get it to us as soon as you can. When we did it, we refrigerate it and we'll analyze it for nitrate. We don't dry it. We analyze it as it is. And then for a further test, we'll dry the sample and do the analysis. For the other test, on a wet sample. But for ammonium, we'll do it on an as-received basis. And the soil can be as dry as anything, but when we receive it, but that's how we're going to analyze.
Do you know of any commercial labs that do some biological tests?
Ward Labs does it in Nebraska,
Cornell.
and Cornell does it.
So in order to make the body nitrate assessment, it's also critical to know what time of day the sample is used.
Yeah, I mean, that'll make a difference. Obviously, in the winter time, things are going to be different than heat of the summer. So, yeah. And you probably, if you were going to assess that each year, you probably would either take tests throughout the growing season and see what kind of how things kind of change, or take a sample the same time every year.